Hi, I'm Rick Schoenberg, and I want to tell you a little bit about my research in case any of you want to, um, you have me as your advisor. I deal with point processes, which are data sets where um, we have the points, meaning like the times that earthquakes happened, or maybe the space and times where people were reported to have a certain disease, like COVID-19 or something like that. Or I've dealt with some other data sets like wildfires and crimes, but data sets where you have a collection of points. That's really what I work on. And all my papers are here in case you want to read any of them, and you can email me if you're interested in working with me. Yeah, a point process is a random collection of points, and a commonly used model is the Hawkes model. I won't get into the model too much, but you have this background rate and then some triggering function embodying the idea that earthquakes, there's some main shocks that then have aftershocks, and those aftershocks have aftershocks, and so on. And similarly, a lot of people for disease epidemics are now using a similar kind of model where some people get in your city or whatever happen to get the disease, and then they infect others, those others infect others, and so on. And some of my applications are to earthquakes, where one of the things I've been working on the last few years is trying to estimate this triggering function, which dictates the distribution of how, of the aftershocks, spatially and temporally, and how many there are around the main shock. And one aspect of that is the temporal, what we call the triggering function. And it's nice to estimate that non-parametrically, that is without assuming, before people were doing it non-parametrically in recent years. Before that, people would fit a curve to this, like maybe an exponential or a power law or something. But it's nice to let the data drive it and just fit this non-parametrically. And that's one of the things I've been looking at. We can also estimate the spatial temporal distribution of aftershocks non-parametrically as well. And here's an application to Ebola data in 3 countries in Western Africa: Guinea, Sierra Leone, and Liberia. Each column represents a country. And just to show the projections and then the actual data's observations of Ebola counts are in red. And this is a forecast based on a Hawkes model in the top row. And the bottom row is what the alternative that epidemiologists like to use, like SIR, they're called SIR models. And our Hawkes models actually fit the data a lot better than SIR models. So I think Hawkes models are going to kind of be the next big thing for epidemic forecasting. And so, yeah, I've been interested in using these kind of models to forecast COVID-19 in various countries. And this slide just compares the fit of these Hawkes models to SIR models. And usually the Hawkes model seems to fit better. This is a compilation of all the papers that I could find where the 2 kinds of models were compared. And generally speaking, the Hawkes model had a lower root mean squared error, so a lower typical error size by about 20 to 40% compared to the standard models, which are these SIR models. So I really think the next big thing is going to be Hawkes modeling in a lot of different applications. And another big area for me is model evaluation, trying to discern which model fits better than the other. And some things I've been looking at are super thin residuals and Voronoi residuals. I don't have time to get into it here, but these kind of graphical methods where you can look at a picture and it can tell you where one model fits better than another, or where one model might be, improved. So that's what I do. And if you're interested in working with me, please email me or track me down, and that'll do it.